Look up at the vast dark canvas of the night sky. What do you see? You see countless stars. You see distant galaxies. You see nebulae, all scattered across an immense expanse. If you could zoom out far enough, you would see these objects are not randomly distributed. They form an intricate and breathtaking pattern, a colossal web of filaments, clusters of galaxies, stretching across billions of light years. Now imagine looking inward, at a map of the human brain. You would see a similarly complex network. Billions of nerve cells, neurons, connected by trillions of thin fibers, forming a dense, mysterious web. The two images, the grand structure of the universe and the intimate architecture of the brain, look startlingly alike. This visual echo sparks a profound question. Could the universe in some way operate like a giant brain? What exactly is a neural network? At its core, a neural network is a system composed of many simple, interconnected processing units. In the human brain, these units are biological cells called neurons. Each neuron is a tiny switch. It receives signals through synapses. Inputs accumulate, and when they cross a threshold, the neuron fires, sending its signal onward. A simple on or off action. The true magic is the number of them, about 86 billion, and the connections between them, numbering in the trillions. This vast, interconnected web gives rise to everything we experience: our thoughts, our memories, our emotions, our actions. The power of a neural network lies in its ability to learn and adapt. Connections are not static. Their strength changes with experience. When two neurons fire together frequently, their connection strengthens. Neurons that fire together, wire together. A memory is encoded across patterns of connection strengths in many neurons. Simple inputs trigger cascades of firing through learned pathways, producing the perception of a familiar face or a beautiful sunset. There is no central controller. Complexity emerges from local rules. We have built artificial versions, artificial neural networks, layered nodes with weighted connections, that learn by adjusting numerical weights to recognize patterns and power modern technologies like voice recognition and medical imaging. Now, let us zoom out from the inner space of the mind to the outer space of the cosmos. On its grandest scale, the universe also has a web-like structure, the cosmic web. Immediately after the Big Bang, the universe was an almost uniform, hot, dense soup with tiny fluctuations in density. Minuscule lumps in the primordial soup became gravity's footholds. Over eons, gravity amplified these imperfections, sculpting today's universe. Matter did not collapse into one clump. It stretched into long, tenuous threads. Where filaments intersect, dense knots form, galaxy clusters, sometimes thousands of galaxies. Between them lie vast voids, hundreds of millions of light-years across. Mapping millions of galaxies reveals a sponge-like web pattern, the backbone of the universe. Its scale spans millions, even billions of light-years. A node here is not a neuron, but a supercluster of galaxies, bound by gravity and dark matter. Connections are not synapses, but colossal filaments of gas and dark matter funneling material into clusters. Unlike fast neural signals, the web evolves on cosmic timescales. Signals are the slow drift of galaxies and gas, orchestrated by gravity and cosmic expansion. Filaments act as highways, channeling gas into ever-growing clusters as voids expand. By measuring this geometry, cosmologists infer the nature of dark matter and dark energy. Reading a fossil record written by gravity. This is the grand structure we now compare to the network in our heads. Why compare systems so different in scale, substance, and speed? Because both can be described as complex networks. The same mathematical tools, especially network theory, apply to both. Network theory focuses on abstract connection properties. Metrics include number of connections per node, average path length, and clustering tendencies. Applied to brains and the cosmic web, the numbers look surprisingly similar. Both balance local clustering with long-range connections. A brain clearly processes information, taking input, routing it through pathways, producing thoughts or actions. Some propose the universe can be viewed as a giant information processing system. The evolution of physical states, particle motions, expansion, and structure formation can be seen as a form of computation. The laws of physics are the algorithm. The universe's state is the data. The cosmic web is the hardware. Others ask if cosmic growth could be recast to resemble learning algorithms, laws adjusting like weights. These ideas are frontier and highly speculative. Quantum gravity models suggest spacetime may be discrete, a network of causal links. geometry and gravity could emerge from connection patterns, much like thought from neurons. The initial evidence is visual, but the case rests on quantitative analysis. In a landmark 2020 study, Franco Vazza and Alberto Faletti compared cosmic web simulations with cerebellum and cortex slices. Beyond resemblance, they applied network theory tools to both. Distribution of matter in the web closely matched neuron distribution. Connections per node and flow patterns showed statistical similarities. They examined memory-like capacity via connection area proxies. The human brain, about 2.5 petabytes. Cosmic web estimate, around 4.3 petabytes. This does not mean the universe remembers, only that complexity is quantitatively comparable. Both appear to be small world networks with surprisingly short paths across many nodes. In brains, this speeds coordination. In the web, it is the most efficient structure gravity could assemble over time. Both show hierarchical organization. Columns to areas to networks. Stars to galaxies to clusters to superclusters. Gravity and evolution converged on nested, scalable architectures. A compelling hint of universal network optimization. It suggests a universal, efficient way to build complex, stable, scalable systems, regardless of substrate. Despite parallels, we must be skeptical. The analogy has clear limits. Neurons are living cells communicating via rapid electrochemical signals, up to 120 meters per second. The cosmic web comprises dark matter, gas, and galaxies. Its signals are gravity and expansion over eons. Brains adapt and learn. Cosmic filaments do not reconfigure to remember. They follow fixed laws and initial conditions. A warm, wet, liter-scale brain versus a vast, cold universe at about 2.7 Kelvin. Physics regimes differ profoundly. Beware apophenia. Many branching systems look alike. Resemblance alone does not prove a deep link. Without a testable mechanism, the universe as brain remains a powerful metaphor, not established theory. Even so, the analogy sparks new thinking. Applying neuroscience math to cosmic data and vice versa. It builds bridges between physicists, neuroscientists, and mathematicians, fertile ground for breakthroughs. It pushes us to ask, what is information's nature? Is complexity a universal tendency? Biological evolution and cosmic expansion may converge on similar architectures when systems grow. Our neural network may be a small echo of the grand cosmic network. If the universe isn't thinking, what is it doing? Perhaps physics itself is emergent information processing, a fresh lens for sky above and mind within. If you enjoyed this, like, share, and subscribe for more.